All right, let's get started. So hopefully today the sound will be better and I won't be shouting. So we'll talk about Matplotlib and visualization today. This will only be like a very short introduction into some basics. For those of you that are in the DSI Masters program, you have like a full lecture just on visualization and exploratory data analysis. So I won't go nearly as deep, obviously, today. But I think visualization is quite important in all data science and particular machine learning. And so I want to go through some very basics for those that are not in the program or just to summarize. Also, I want to go through some specifics of Matplotlib. Matplotlib is the main visualization library for Python. I think the DSI course is taught in R, and Matplotlib is quite different. It's sort of was originally modeled after MATLAB, and you can do any visualization you want with it, but it might take a little bit more code, which is sometimes a little bit annoying. So I want to start with some principles of data visualization, again, just very broadly, and then talk in more details about how to do things with MATLAB. So what are the reasons we do data visualization? I think there's two main reasons. One is that we want to explore what is happening with our data set. We want to look at the data. We want to figure out what are the properties of the data set. And the other is to communicate to someone else what we think is going on with the data set. So in a paper or a report, or even just showing to your boss a plot, you can tell another person what you think is happening with the data, or how well your model performs, or why you lost a lot of money. And so I think these are the two main reasons, and you want to use slightly different tools for these two. Particularly if you want to use data visualizations to communicate, you often put some more care in than if you just do it for yourself. But I want to argue today that even if you just do visualizations that are sort of very quick visualizations, you should put in some effort into making sure your visualizations are good so you can draw the right conclusions. Very often when I mentored the capstone project for DSI in the last couple of years, very many reports had like a figure and it was like, here's a bar plot of X, or here's a scatter plot of this thing. And that's not how you should do data visualization. There should always be a story behind why you're showing something. And if you show a plot, it should always be clear to the reader why you're showing this plot. So if you show me a bar plot and say, here's a bar plot, that means nothing to me. What should I be looking for? Is something surprising about this? Is there something obvious about this? Usually you have a question in mind when you show a visualization. And so you want to show something either to maybe to confirm an intuition or to show something surprising, but there should be some sort of question or some narrative behind it. If you just show me like a plot without telling me why I should look at the plot, I'm not going to look at the plot. And if you do this in your report, I'm going to like argue with you about it and give you worse grades. So, but it's also very important if your later report writing is very important for all kind of data scientists. Or if you're a scientist, clearly you want to write papers. So whenever you do visualization, visualizations can be very, very powerful. But you need to make sure why the reader should care. Like you need to tell them what is the story behind this graph, not just look at my graph. So after saying this, I want to start with a couple of quotes from famous data visualization people. So this one is from Edward Tufte, who is sort of the godfather of all of statistical visualization. He has some great books and articles about the topic. They're a little bit dated, but still totally worth reading. And so what he says is, above else, show the data and maximize the data in ratio. So what you should focus on is really show what the content of the data is. You shouldn't focus on your fancy method or make it look super nice. You should first focus on actually showing what is the data. And when he says maximize the data ink ratio, he said what he means is to make sure that most of the ink, even if it's like digital ink now, for him it was actual ink, for us it's usually pixels now, most of the pixels show actual data. If you have something drawn on your figure, make the thing that's being drawn data or useful for data. So don't have like too many grids and ticks and things that are redundant, basically. You definitely want to label your data, something I'll come back to later. So you want to make sure you have the ticks labeled, and you have the axis labeled, and you have the legend, and so on, but you don't want to put in things that are meaningless. And a lot of plots, unfortunately, particularly if you do it with Matplotlib by default, there's a lot of sort of meaningless craft in there, and you want to get rid of that. You want to show as much data as possible, given sort of the amount of ink that you use. Another quote that I quite like is from William Cleveland. He also wrote a great book about data analysis. It's also a little bit dated, but also still great. And he said, tools matter. For him, this was methods for doing visualization, like using LUS or something like this for smoothing. And I think he's right, definitely. Which tools you use for your visualization, whether you use a Lineplot or a Barplot or whatever, matters a lot. But I also think software tools matter. And it really matters whether you know and you understand how to use your tools and what tools you use. Arguably, Matplotlib is maybe not like the most convenient tool for doing data visualization. I'm going to talk about a couple of other tools, but it's definitely a tool that you will get in contact with wherever you work. And I think it's important that you understand how it works, that you can really achieve the right plots. And to finish this up, also my 2 cents, which is always label all stuff. When someone comes to me with a figure that's not labeled, I tell them do the figure again. It's a very terrible habit not to label your X and Y axes, or not to do legends, or not to label the different graphs. And so always make it a habit to always label everything. Otherwise, you might forget yourself what a graph is showing. Also, spend more time on your graphs. So when I publish a graph somewhere, it usually takes me about an hour or 2 to come up with that graph. And I'm pretty decent with Matplotlib. The things that are here in the lecture, anything that's on a slide probably took me about half an hour to make, usually, unless I was really in a rush. So if I can, I spend half an hour on every figure you'll see in a slide. So if you spend like 1 minute on a figure in your homework, you're not spending enough time. If you want to use the right tools, if you want to tell a story, you should think about what is the story behind this, how can I best show it? And so for your homework, I say at least spend 10 or 20 minutes on any figure you do. If you write a paper or a report, probably want to spend an hour thinking about what is it actually that you want to show and how do you best show this and make it look polished. All right, so this was a very high-level overview. Now I want to talk a little bit more about how do you do data visualization. And so the first thing I want to talk about is visual channels. So here, this is an overview that I lifted from a thesis called Systematizing Glyph Designs for Visualization that I linked in the online material. And I kind of like the introduction to this thesis, so I'm stealing stuff from there. So visualization usually means you have data with different properties, say like features. So you have a multivariate data set, and you want to map this somehow to a figure. And usually for each quantity that you want to visualize, you can map this to one of these visual channels. So here you can see length, angle, curvature, shape, area, volume, lightness, saturation, transparency, color, texture, position, motion, blur, containment, connection. So these are like a lot of them, and you don't really use most of them most of the time. So the ones that there's like some work that shows which of these are the most efficient, and these are actually the ones that we use most often. And so very efficient is position, which is what we use in nearly every plot, like in a 2D scatter plot. So you have the x-axis and the y-axis as two of your scales, and you map some data property on the x-axis and some data property on the y-axis. Another one that's very efficient is length, so which we use in Barplots. Oh, maybe I should say, so this means efficient in terms of cognitive processing. So they show people plots and they test whether people understand what's in the plots. They ask them to, is this or this quantity bigger? And they see if the people that look at the plots can tell correctly what's happening. And so that's what they were measuring here. And so that's what you want to do. You want to make sure that whoever looks at your figure can correctly interpret the data. So yeah, we have position and length. Angle is works less well. Then area, which we use in, for example, pie charts, which actually are not that great. Volume is even worse. Texture density, color saturation, and last of all, color hue. So maybe this is actually for this experiments are for continuous data. So for a quantity, if you want to visualize a quantity, don't use color hue. I've seen a poster where someone visualized for the New York bike rental data set, like here's how many rentals there are for men, and here's how many rentals there are for women, and they said, oh, you can see that, so this was like a map, a 2D map with hues, and they basically said, well, in this area, the ratios between men and women are different. So what I needed to do to get this statement from these maps is I need to take the color hues, and I need to compute the ratio between two hues. I have no idea how I was supposed to do that. So hues is not something we can really compute with. And so hues are very good for if you want to do categorical data. So one line is red, one line is green. That's great. If you want to tell me how much something is a quantity, hues are terrible. And saturations are somewhat better. We'll talk more about colors in a little bit. Yeah, it's also interesting to think about what are sort of the pop-out effects. As you can see, like some channels have more a better way to pop out. So here you can see that obviously color has a very strong pop-out effect. Orientation, also the end size, whereas here proximity maybe less so. Motion you can't see. If it was animated, motion would have like an incredibly strong pop-out effect. Here's an example from a book that I also referenced, Fundamentals of Visualization. So I actually highly recommend that you check out this book. It's still a draft, but it's a draft of an O'Reilly book that I linked in the materials. You can read it online for free. It's written using R, but there's no code in the book, so it doesn't really matter. It talks more about the principles. So here you can see a visualization of actually a 5-dimensional data set of the fuel efficiency of different cars. So this is like standard toy data set. And you can see that he used 5 different channels for these 5 different things. So there's the engine displacement, so like basically how big the inside of the engine is. On the x-axis, the fuel efficiency in miles per gallon on the y-axis. Then he uses both lightness and hue to use power, so how strong the engine is in horsepowers. The weight of the the weight of the car in 1,000 pounds is the size of the dot, and then the number of cylinders is the marker. So here, I think this is a very good way to illustrate how you can use these different channels. I probably wouldn't use 5 channels in an actual visualization because it's quite busy and it's quite hard to understand all of these at once looking at the figure. if you focus on some of the aspects, you can like see what's happening. So you can see that basically there's only one very light car, and the only light cars have very small engines. They're over here. You can also see that there's the number of cylinders basically perfectly correlates, or nearly perfectly correlates, with the displacement. So 4 cylinders is here, 6 cylinders is here, and 8 cylinders is here, and so on.
You don't see the mouse.
You don't see the mouse. Sorry. Here. So here, these are the small, there's only very few tiny cars. These are here, and then here you can see 4 cylinders, 6 cylinders, and 8 cylinders. So you can see quite a lot in this visualization, but it's kind of hard to take it all in. And so usually I would use like maybe 3 or maximum 4 channels. But it's a good way to show like these different visualizations. Also here you can see that the horsepower was done as a continuous variable, whereas weight is actually discretized, and cylinders is done as a categorical. So these are not really like this diamond, triangle, and circle. These are not really ordered, even though this number of cylinders is kind of ordered. So I want to talk a little bit more about color maps, because I think they matter quite a bit. Here are some of the color maps that are in Matplotlib. And you can see that there's basically 5 different kinds that they distinguish here. And so I mostly care about color maps for doing continuous, for visualizing continuous quantities. If you have something quantitative like categorical data or like different curves, you can use a quantitative color map, and there's like different ones, but they're all like pretty fine. I think by now people mostly use either the Vega 10 or Vega 20, depending on whether you want 10 different colors or 20 different colors, or you can use like a color brewer one. And that's sort of pretty easy, and you can also very easy optimize the contrast between these two. But very often people use colors to visualize continuous quantities, most commonly in heat maps. And so depending on what you want to show, you really should use specific kinds of color maps. So here in the top left, there's sequential color maps that basically go from light to dark and between 2 hues. Only the cool one actually doesn't go from light to dark, it goes from light to dark to light. There's diverging color maps, which basically have a set center and go in 2 different directions from there. And then there's miscellaneous color maps, and this is actually what you used to see quite a lot. So here this jet and rainbow are color maps that you probably have seen before, but they're actually really, really terrible for reasons I'll explain in a bit. Here at the bottom you can see new color maps. So this is what is the new default in Matplotlib, and some other color maps that they created as part of the research of getting a new color map for Matplotlib. So if you have just if you care about the endpoints more, you should have something that is sequential. If you care about the midpoint, you should use a diverging color map. And you should basically never use one of these color maps. And the reason is the following. So this is from the research they did for creating a new color map for Macroflip, and it's quite great. There's a talk on YouTube that's called Creating a New Color Map for Matplotlib, I think, by Stefan van der Walt and Nathaniel Smith. And it's great if you want to look at it. So this is a color map called gray. It maps the value to its intensity in gray. Here, there's 3 example images on the right. These are 3 different heat maps, basically. This is low resolution. These 2 are high resolution. You can sort of see what's going on. The things on this side are just the color map. And then this is the lightness deltas, which means how much does the lightness of the color map change if I change the value? And you can see it's basically a straight line. So this means the derivative of the color map is basically constant. So if you go from 4 to 3, the change is the same as if you go from 3 to 2, which is what you want. You can also see here the color map in the three-dimensional, I think this was the lab space. Yeah, I think it's lab. So this is like a three-dimensional color space that's more similar to human perception than what RGB is. RGB is not a very natural color space for humans. So in here you can see two of the other color maps. So Jet, which was previously used in Matplotlib and was also used similarly in Matlab, I think, or a similar one at least. And on the right you can see the new color map, which is called Viridis. And so one thing you can see is that, okay, there's so many things going on. So here you can see that the derivative is not constant. So the changes between intensity are very, very different depending on where you are. What this leads to is that it looks like there's edges in the data where there's not really edges, because there's edges in the color map. So if you look at this guy, or this guy is even more intense. So here, it looks like there's like a red center, and it looks like there's an edge around the red. At least to me it looks like. It looks like to me like there's an edge around this light blue. There is no edge. It's this spike in the color map. And that's actually very terrible. Your color map shouldn't make you think there's something in data where there's nothing. And if you look at here, this new color map was designed to be perceptually uniform, so you have like constant deltas, and so basically this is a straight line, and so you don't get these weird edge artifacts. Another thing is that you might want to think about is thinking either about printing or colorblind people. If you print this, it's going to become this, and it's going to become completely unusable. Or if someone is colorblind, it might also become something like this. Here, this map just goes from dark to light, and so even if you just print it, it's going to look nice. Or if someone's colorblind, they'll still be able to understand it. Whereas here, the brightest points are two like completely arbitrary places somewhere in the middle. So never ever use Jet or a similar color map. Always use perceptually uniform color maps if you want to show continuous quantities. If you want to use or to show categorical quantities or discrete quantities, this one is maybe not the best because I mean it's all blue and green, and so there could be more contrast in there if you used more colors. All right, so this was all I wanted to say about like general principles for visualization. After talking about Matplotlib, I want to talk briefly about some do's and don'ts also. But before we go into this, I want to talk about Matplotlib. I already said some things about Matplotlib, so I think it's great. The problem is it doesn't have a lot of very good tooling specific for doing data visualization. So I sometimes say my book that's about machine learning has more Matplotlib code in it than scikit-learn code. And it has more Matplotlib code in it than scikit-learn code by like a factor of 5 or something, because it takes much more code to do things in Matplotlib. But you're very free, you can do anything you want, but it requires a little bit more code. Oh yeah, so one thing that, even when you start, I don't know when you guys started installing your environment, some people are still using Matplotlib 1. Matplotlib 1 has this terrible color map. Matplotlib 2 changed all the styles, and it looks very different. And now there's Matplotlib 3. You should definitely make sure that you use Matplotlib at least version 2. Because the Matplotlib 1, the figures will not show correctly in newer versions, and everything will look terrible. But yeah, probably if you all recently downloaded Anaconda, which I really recommend you do, should all have Matplotlib 3 and everything should be fine. So there's a couple of other libraries you can use in Python. Actually, half of them are built on top of Matplotlib to do more data visualization. One that you might use pretty commonly is Pandas. So Pandas has some plotting tools in there. I think actually the Pandas developers would prefer if they were not in Pandas, but they were somewhere else. But I don't think anyone wants them right now. This is basically an integration of data frames with Matplotlib. So there's some convenience things. It labels the axes for you using your column names and things like that. And it has things like a scatter matrix. And so there's like some nice tooling in there. You can do like a bar chart with like, you can do like a box plot that looks reasonable in a single line. Wherein if you just use Matplotlib directly, it may take more time. There's also Seaborn. Seaborn is also built on top of Matplotlib, and it's much more inspired by like statistical plotting. It's very powerful and very thoughtfully designed. Sometimes I find it a little bit hard to use, and I find it hard to adjust it to do the way I want to do things. Given that it's on top of Matplotlib, even if you choose to use Seaborn, which might be a good idea, knowing Matplotlib really well will help you because everything in Seaborn is just built using Matplotlib. Then there are several other packages that are not built on Matplotlib. Mostly there's Bokeh, which is basically built as an alternative for Matplotlib for use in browser and in Jupyter, that renders to JavaScript. It's still a little bit sort of, I mean, it's been like 5 years old or something, so I don't think I can call it experimental, but I think it's not as fully featured as Matplotlib, and there's still some glitches in there. Also, if you do things in JavaScript in the browser, if you put 1 million points in the browser, your browser is going to slow down. If you put 1 million points in a PNG, it's fine. It's just pixels. Because in JavaScript, usually, unless you're doing something smart, there's Bokeh data shader, which does something smart, but unless you do something smart, if you inject each data point as an element in your JavaScript in the DOM, this will be very slow. But sometimes it's fine, unless you have a lot of data. There's several translations for ggplot to Python. I don't know which one is the newest right now. There were at least like 4 different ones so far. There's a library called bqplot, which is also using JavaScript and widgets to do interactive visualization in a Jupyter Notebook. This is mostly for time series. This came out of Bloomberg, so I think Bloomberg developed this internally to do financial time series analysis, and then they open sourced it. So this is quite nice if you're into that sort of thing. Plotly is a startup that does basically an API for visualization. They have their own internal stuff. It's very nice, but if you're not online and if you can't talk to their server, you can't do visualizations, and it's all closed source, and if they get bought and the product goes offline, your code stops working. So I don't know. It's very convenient, though. I have not really used it, but I know a lot of people like it. Altair is relatively new. It's done by Jake Vanderplas, whose book I recommend to you all the time. It's meant to be much easier to use than Matplotlib, so it's a complete replacement basically. For rendering, it actually uses D3, so it also uses a JavaScript-based renderer. And it allows you to do more like cool interactive stuff, and the idea is that it gives you very nice, like beautiful looking plots without worrying too much about the details. But it's still like pretty new, but it's probably worth taking a look at. And finally, I wanted to mention Yellowbrick. They have some plots. So this is all, Yellowbrick again is also built on top of Matplotlib. They have some tools for plotting stuff in scikit-learn. Scikit-learn estimators, like feature importances, and so on. So these are like some helpful functions to do plots that are commonly done in machine learning with scikit-learn. So I'm going to talk about basically none of these today. I'm only going to talk about pure Matplotlib, but I think that's a very good foundation for learning more plotting libraries in Python. Also, definitely for talking more about Matplotlib, Jake's book, the Python Data Science Handbook, is a great resource. I really highly recommend you look at Jake's book. So first to start, you usually need to import Matplotlib. Please don't do it like this. Never star import anything. Star importing makes it harder to read your code and makes it also impossible for any linting tools or code analysis tools to know what's going on. So the standard import is import matplotlib.pyplot_splt, which is a little bit of a mouthful, but just do that. Don't do anything else. So for the homework, for this first homework, you're going to be writing Python scripts. If you do this, you actually have to do plt.show at the end to show a plot. Most of the class we will work inside Jupyter Notebooks. And so I want to spend some time on how Matplotlib interacts with Jupyter. So because this is probably where most of your visualizations will be done. So to have things show up in Jupyter, you have to use one of the Matplotlib magics. So a magic in Jupyter is something that starts with a %, and it is some Jupyter internal command. The sort of, I think, oldest possibly, and maybe most robust, is Matplotlib inline. What Matplotlib inline does is basically Matplotlib creates a PNG and sends it to the browser, and the browser displays it. Whenever you call any plot command, or for each new cell, it will create a new figure, and it's not possible to change any of the previous figures because you just have the PNG. You can redo previous figures, but you can't change anything in the figures. There's no interactivity, there's no panning or zooming, because you literally just have the PNG in your browser. So basically, none of the nice plotting zooming features, but it's very robust. There was something called Matplotlib Notebook, which was interactivity for the old notebook. So I didn't really talk about Jupyter that much. I don't plan to, but so there was the Jupyter Notebook, and now there's Jupyter Lab. I think you should all use Jupyter Lab. Jupyter Lab is much nicer, and it's more of an integrated IDE than the Jupyter Notebooks were. However, Matplotlib Notebook doesn't work in Jupyter Lab anymore because for security reasons, Jupyter Lab doesn't allow JavaScript. The good things about Matplotlib Notebook was that you, well, on the one hand, you need to create separate figures, but on the other hand, you can upgrade existing figures, and you can use all the panning and zooming and resizing and everything that you want. If you're now in Jupyter Lab, you can use Matplotlib widgets. So again, you can do all the panning and zooming and interaction and so on. You can update existing figures. Again, you need to create separate figures explicitly. So what I mean by this is, if you have a cell and you create, say, plot X, and make a new cell and say plot Y, the plot Y will update the first figure and will plot the Y in the same axis that you plot X in, which might be surprising. You say plot Y, nothing comes out. It's because it updated the previous figure. If you want a new figure, you need to do plt.figure. So anyway, Matplotlib widget is the new way to do it in Jupyter Lab. You need to install some additional add-ons though, and there's a link to the installation instructions. So if you care about having panning and zooming and reshaping in your figures, you should use that. All right, so next, really Matplotlib basics on using things. So the main concepts are a figure is usually a window or an image. So it's one thing that pops up, or one PNG or SVG that you store. And axes are things that you usually have coordinate systems and you draw within. And usually each figure by default has one axis, but it can have multiple axes. These are usually called subplots. So here you can see there's one figure, there's two axes. The inside of these axes have this map, they have like all the stuff, and there's like a color bar attached to each of these axes. And so you can't really draw directly on the figure. Usually you draw on an axis that's inside the figure. So how do you create these things? The easiest way to create them is just you don't create them and just start plotting. If you should start plotting, it will create the first figure automatically, and it will create an axis in the figure, and then we'll start plotting into this axis. And so if you do plot x, it will create a figure, it will create a single axis, it takes all of this figure, and will plot x inside this axis, and you don't have to worry about it. And that works as long as you only want one figure. If you want the next figure, like each plotting command will work on the current figure. And so if you want a second figure, you need to create explicitly. To create a figure, you can do plt.figure. In this call, you can also change the resolution and the shape of the figure, for example. And this will create a figure, and it usually has like, I think by default it has a single axis object in it, and it will set the current figure. So, as I said before, Matplotlib is sort of was originally inspired by Matlab, and which has like a little bit of an idiosyncratic design where there's this concept of a current figure and a current axis. If you draw, give me 1 second. Do I have slides on this? No. If you draw and you don't tell it where to draw, it will draw in the current figure and the current axis. And that's always the thing that you created last. And do I really not have? Give me 1 second. Yeah. Okay. Again, I don't have a super nice illustration of this. But if you do pltr figure, it will create a new figure. It will make this new figure the current figure. Another way to create a figure that I use quite often is plt.subplots. That creates a grid of, so that creates a single figure that has a grid of subplots n times m. So here the thing on the right-hand side that you can see is created by doing plt.subplots 2, 2. And this returns a single figure and the numpy array of axes. So here, if I do 2, 2, axes will be a 2 by 2 array of axes, and I can plot into these individually. All right, so this is how I can create figures. The subplots command creates figures and subplots. If I already created a figure, I can also add more subplots later. And again, there's kind of two ways to do this. One is I call plt.subplot nmi, which says that at position, in a grid of size n times m, it will plot at position I. So I goes from 1 to number of possible positions. So this is basically straight from MATLAB, and so it's kind of weird why it starts with 1. But so you will see some people do this. So basically here, if I want to create these four this 4 subplots, this 2 by 2 grid, I can do plt.subplot 2 to 1, plt.subplot 2 to 2, 2 to 3, 2 to 4. So we'll create these 4 subplots. And actually, the commas are optional. So I could actually write subplot 221, 222, 223, 224, but I think that's super confusing, so I never do that. And this is equivalently, I can create all of them at the same time, and plt.subplots 2, 2. And then I get an axis object, and this is a student numpy array. one of the reasons why I might use the first one sometimes is when I want more complex layouts. You can also do something called the grid spec, but I'm not going to go into grid specs. But if I want a layout like this, often what I do is I say, create a subplot in a figure in a 2x2 grid, give me the first one. In a 2x2 grid, give me the second one. And then in a 2x1 grid, give me the second one. So I pretend I changed how the grid looks, and then it gives me these kind of figures, which sometimes is nice. So now I don't have like a regular grid, but I can do this in some other way. So there's really two kind of interfaces. One is sort of this MATLAB-inspired one, and the other one is object-oriented. And some of the commands are more for the MATLAB-inspired one are more for the object-oriented one. So the MATLAB-inspired one, basically, you always plot in the current axes. So at the top here, say, wait, is it missing something? Yeah, it's missing something. Where's the sorry, the red curve is missing. That's sad. But okay. So here, in the first one, the first one is the MATLAB-inspired one, where basically you create a subplot, and then you plot into the thing that you just created. And so plt.plotSyn would plot in the first thing in this 2x2 grid. Then I create the second one, and I plot into the second one. So here you have the stateful interface where you keep track of what is the current subplot. In the object-oriented interface, I create all of them at once, and then I actually use the axis object, and I call plot on the axis object. So here, this plt.subplots gives me this 2x2 array of subplots, and then I can index this and call plot on the axis object. So axis 0, 0 is the top left axis. I can call plot syn on this one, and I'll get something plotted in the first quadrant. And I totally blame my TAs from last year that I put in the wrong figure. Sorry about that. And so you can mix and match these two, basically the stateful and the non-stateful. Usually, if I have a single subplot, using the statefulness is okay. I don't need to keep track of the subplots. If I have multiple subplots, I usually like to keep track of the subplots. One issue, though, is that all the commands look different. The plotting commands look the same. So you can see here at the top, doing plt.plot and axis.plot looks the same. They're both called plot. For all other commands, they're different. So if you want to set the title of an axis, it's either plt.title or axis.setTitle. It's plt.xlim to set the limits of the axis, or axis.setxlim. So usually for the object-oriented interface, there's a set underscore before it, but there's also other like subtle differences. So be aware. Some things you can only do with the object-oriented interface. The object-oriented interface is maybe a little bit more verbose, but it's much more powerful. And so sometimes you created your plot with sort of the MATLAB interface, but then you realize you want to change one very specific thing. And so if you do that, you can get the axis object that you're currently working on by doing plt.gca for get current axis, or the figure that you're currently working on using plt.gcf. And so then you get the object back on that you're working on, then you can modify that object. So these are in particular, the GCA is very useful if you just start plotting and then you want to change something to the plot that you already made. Yeah, but always sort of be aware of these two interfaces and think about which one are you using right now. Are you explicitly handling the axis objects, or are you just working on the current axis and current figure? And that took me too many years to figure this out, and I hope it takes you not as long. I want to talk through some of the basic plotting commands, just very briefly, hopefully. Wait. I always forget when the lecture ends. 20 past, right? 25? No. 25? Okay. Good. Probably going to finish a little bit early today. We'll see. Okay, but if you should look at the gallery and the plotting command summary. Both of these are great resources to figure out what plotting commands there are and how to achieve a particular look with Matplotlib, which might not be entirely obvious. So the gallery shows you many, many, many different plots, and you can click on the one that looks most like what you want, and you can copy and paste the code. So here, one of the easiest one is plot. Plot is usually used for line plots, and so you can either have, as in the first example, I can just plot something. This will be plotted as the y values, assuming the x values are just enumeration. So here, if I just give one thing, this is going to be the y values. So this is equivalent to doing plot, then a range, and then this. So here you can see these plots are completely identical, so by default it just assumes the x values are 0 until the number of points you have. And so but you can also obviously give explicitly x values and y values. So here I just gave integers. You can also just give a linear space here. This is actually was the input for the sinus. You can, if you don't want to actually want to do line plots, but you just want to do a scatter plot, you can do a scatter plot with the plot command by just changing the symbol. So here, or the line style, I should say. So if I put the line style to be O, then it makes circles. If I use dot, it makes dots. Here's some other line styles. If you do dash dash, it makes dash lines, dash dash O, dashed lines and markers. This is sort of a very simple way to change the line style. You can also here C is color and LW is line width. And so all of these are useful. If you just do dash O, it does a line, but it also marks where the points are. Sometimes if you have a plot like this, it's good to know where the points are. So I sometimes like to do something like this, where I also either put a dot or an X at every place where there's a point, or you can just put a tick. Because if you have a long line, you don't know if there's just one point in the end, beginning and one point in the end, or if there's 100 points on the line. You just plot the line. So often it's helpful to show where the points are on the line. Oh, there's a slight idiosyncrasy you could see in this if you paid close attention, which is here I say subplots 4,5, which says there's 2 rows with 4 columns each, and the figure size is 10 by 5. This is screen inches, and they're in the other order. So it's rows, comma, columns, width, comma, height. And it has been confusing me ever since. I should ask the Matplotlib maintainer why they do this to me. But it probably wasn't him, it was Matlob. Anyway. Another thing that I used here is plt.titleLayout. It's basically a hack that makes the subplots fit well into the figure. By default, often the legends overlap or like the title overlaps and so on. TitleLayout is a nice hack. They also have a new option called constraint layout, which actually does the right thing and does a layout optimization. So it does like a linear optimization problem to try to figure everything and fit everything into the figure. So I also highly recommend to use their constraint layout feature, which is not on by default yet. So the thing that I probably use most commonly is scatter. So scatter is actually meant to scatter continuous quantities, and so you can see this is a scatter plot with scatter. This is the same plot with plot O. They're exactly the same. So if you have just a single thing, you can either do scatter or plot. It doesn't really matter. What scatter also allows you is to use some of the other scales, the other mediums that we talked about earlier. So I can use, say, color or size. So here, for this one, I say the color is x minus y, so everything on the diagonal will be white, and everything above the diagonal will be blue, and everything below the diagonal will be red. Here I used BWR, which is like a diverging color map, so white is in the center, and I know where the 0 is. And I can also, so this was just color, I can also do size, and I think I can also do different markers for different points. So if you have a continuous quantity that you want to vary with each point, you have to use scatter. Sometimes I also abuse scatter to plot different categorical things, like the 3 classes in the iris data set. And you can do that by doing c equal to y for the classes. But the problem is that's not really what it's meant for, and then it's basically impossible to get the right legend. And I've been struggling with this for many years now, and there's still no nice solution to how to make a scatter plot with categorical data. So the actual way to do it is to call plot or scatter 3 times, and then have a legend explaining this is one class, this is the other class, this is the third class. Question? No. All right. A couple other things. Histograms, obviously, are there. Pretty straightforward. Usually, you want to adjust the number of bins. I think by default, the number of bins is still, I'm not sure, it might be still 10. Maybe I changed it to auto now. But I think it looks like it's 10. So usually you want to have more bins. Clearly, if you add too many bins, it becomes too noisy. So there's an auto option, and the auto option tries to figure out, there's actually several different algorithms that are implemented to automatically figure out what is a good bin size, and if you're lazy, just use that. Otherwise, play around with what looks good. But usually the default, I think if the default is still 10, it's usually too coarse. There's also barplots. Barplots actually, are like slightly tricky sometimes. Here, this is, I know these are movie attendances, but I don't know where I got them from. Like, what year is this? Was this 2007? It doesn't make sense. Okay, so to do bar plots, you use either bar or bar H for horizontal bar plots. You need to give it first the X position for bar or the Y position for bar H, which usually is just a range, and then the quantity for which, then this is the height of the bars. So usually here I do range len, number of these things, and then the gross. If you use pandas, you can just do pandas.bar, and it does it for you, and it also does the labeling for you. Here I do the labeling manually with x tags, x ticks, where again I give it a position on the x-axis and then the name. And I also tell it to rotate. I think by pandas, by default, it's rotated to 90 degrees, which makes sense. If I don't rotate these, all of them will be overlapping, which is what it's going to do by default, and it's going to look terrible. Often because my ticks for bar plots are pretty long, I actually prefer to do horizontal bar plots. So here in this example, I find this is much easier to read than this. But somehow I always have to mess around with the font size so that it looks nice. So here you can see it. You can either adjust the font size or you can adjust the figure size, because the font sizes are absolute while everything else will be scaled with the figure size. So if I do this figure here and I make the figure be larger, so I don't know what it is by default, but let's say I make it larger to 20 inches by 20 inches, the bars will still look the same because they will be scaled to the size of the figure. But the font will be much smaller because the font size is absolute in inches. So I can either make the font smaller or the figure bigger, and it has the same effect, which is kind of interesting. Another favorite that I often use, heat maps. You can use either macho or imshow. Usually I would use, they're like very slightly different. Usually I use imshow. One thing that was changed was that in Matplotlib 1, imshow had interpolation by default, which was turned off. And interpolation actually can be very confusing. So here, this is the data. This is the Veritas color map. So here I have the data. Here is the same data, but it's smooth. So this is interpolation. Smoothing just makes the up data that was not there before. So it looks like there's like very intricate things going on when actually this was all the numbers you had. So usually smoothing is not a good idea because it kind of hides what's actually happening. Also, you might get artifacts. Like, I feel like there's like a thin line here that looks like an artifact. So here for this data set, this is actually the difference of two Gaussians, I think, and one is positive and the other one is negative. And oh yeah, you can see this here in the color map. So the choice of color map here kind of matters. So here in this case, 0 is meaningful because 0 means there's nothing going on, and then one of them is positive and one of them is negative. So in this case, using this diverging color map makes a lot of sense. So here we use a gray color map. Like, most of the background is gray, but it doesn't really mean anything. So this I find harder to read than this, where I know red is negative and, red is positive and blue is negative. If I do that, I actually want to make sure that the white ends up on the 0. Usually Matplotlib will do the try to maximize the use of the color map, and so this doesn't necessarily mean that the 0 will be white. So what I did here is basically, I know the 0 is in the middle of the color map, so I told it pretend the values are between minus 1.5 and 1.5, and then I know 0 will be in the middle of this, and then the background will be white. Otherwise, because of like weird rounding issues or something, the background could be like orange, and that would be very confusing. But yeah, heat maps, I think, is where color maps matter the most. And yeah, you can think about like how these different heat maps look to you and how easy they are to read. And I didn't put jet on here. If you did this in jet, it would be way worse. All right. And another thing that I wanted to highlight, which is maybe less common but very useful, is for this problem. So very often we have lots of data if we're lucky, and then if we scatter data, we get plots like this. So this is called overplotting. So here in the first plot, I just scattered a two-dimensional data set, and basically you have no idea what's happening because there's points everywhere. One way to sort of address this is to adjust the alpha and so make the points semi-transparent. So if I do that, here I can see, oh, most of the data is actually on the cross, and there's only a little bit of data lying here. And I can also see the data becomes more and more dense with 0. And if I change the alpha again, I can see, oh, really, basically all the data is just in 0. But so this is sometimes a nice hack or a nice trick, playing with the alpha, but then it's unclear what is the right alpha value to show what is happening in the data. And so you can play around, you can try different ones, and maybe you find something that works. But there's a better way to visualize this. Any ideas? Anyone looking at the slides and clicking forward? It's hex grids. Hex grids are amazing. Basically what you want to do is, can someone turn off the light maybe in the front? Does anyone know how to do that? Nope. If not, also not that bad. So, nearly? Ah, sweet. Why didn't we do this an hour ago? So, hex grids are basically 2D histograms. Here in this case, it's called a hex grid because the cells in which you do the histogram are hexagonal. How do you pronounce this? Doesn't matter so much. You can also just do squares and just do a 2D histogram basically. And so then I can use these 2D histogram and do a heat map of this. There's actually like some slight issues with this in Matplotlib, and it's not as nice as I would want it to be, but it's better than either of these. So here I'm actually saying use the logarithm of the bins, which in this case I think shows best what's happening. And so you can see here that now for each point in the space, the count of how many data points lie in this particular bin is shown with a color map. And so this is the logarithm. So you can see that here there's like exponentially more points than everywhere else, but you can still sort of see this cloud of points over here, and you can basically see like some individual points still. And so this is a very nice way to overcome overplotting. And so I hope none of you ever shows me a plot like this. This sometimes can be helpful, but usually I would look at this and I would also look at like a hex bin. Yeah?
Is it usually fair to use log?
The question is it fair to use log? And I don't think there's like a general answer to that. It depends what you care about in your figure and what you want to show. Yeah, it would put different emphasis. I don't actually have the figure without the log, but it would look pretty different. I think actually without the log, it would show just a single point in the center because it's just so much larger than everything else. Another cool plotting trick that I very often use is twin axes, most often twin ax. So here, this is a solution to your homework, so take note. So very often you want to compare things in a plot that are not on the same scale. And so here, this is actually, I think from the same website that's in the homeworks, the Spurious Correlations. This is math PhDs awarded per year and revenue made by arcades in that year, which clearly highly correlate. And so if I plot both of these on the same scale, the revenue by arcades is in the millions, the math PhDs probably awarded in the US, is in the like hundreds or thousands. So if I do this, I would have one straight line at the top and one straight line at the bottom, one for the revenue and one for the math PhDs, and it would show me anything. So what I do here is I create a twin axis. So I have x1, which is the first axis in which I'm going to plot the PhDs. And I'm going to do x2, which is a separate axis, but they share the x-axis. That's why it's called twin x. So they share this year scale. And so in the second axis, x2, I'm going to plot the revenue in red. And and so I can show both of these, and I can show their correlation, and I see that there must be some causation between these, obviously. I didn't realize that the actual complete solution was on the, well, it was already last year. All right, so two more things that I wanted to mention that are quite related to this is things that you need to think about when you make these plots. The first thing is aspect ratios. So here, this is stolen from this block you can see at the bottom. I hope they don't sue me. It's the same plot 3 times with different aspect ratios. Matplotlib will always use the same aspect ratio by default, which looks something like this. And you can change the aspect ratio by changing the figure size, or if you have an interactive plot, you can just drag the edge and give it a different shape. So the difference between these 3 plots is just how much did you drag the edge, or how did you set your figure size. But they tell possibly very different stories. And this is actually quite an interesting blog post because it's about what's called banking to 45 degrees. It was a paper by the guy Cleveland, who I cited earlier, that they made a perceptual study that said the graph is easiest to read if most of the lines are around 45 degrees. And so then there was you could have methods to make sure that you have an aspect ratio that so most of the lines are close to 45 degrees. Turns out 20 years later or something, there were actually issues in their methods, and maybe the study is not as clear as it was, as they said it was, but possibly banking to 45 degrees might still be a good idea. That would probably give you something more like the top left. In general, it depends a lot on what you want to show with your data. But the main thing that I want to convey is think about the aspect ratio. And Matplotlib will give you something you call plot, and it will give you a plot. But there's no reason why this plot should have the right aspect ratio for the thing that you want to show. And as I tried to allude with the twin x already, if you add new data to your plot, the data will be scaled differently and may completely change the aspect ratio. So if I have a plot like this, and then I add, this is some money over a year, and if I add something else that's at 10K for the whole year, this plot suddenly will look like this. It will get smooshed down. And just by adding data, I completely change how the plot looks. So always beware of the aspect ratio. The other thing you should be aware of is baselines and scaling of the data. So again, here, these 2 plots, this is another blog post from the same site. These 2 plots show exactly the same data. The left side is with 0 at the baseline. The right is with the minimum value at the baseline. Matplotlib will show you the right one by default. Which of these is the true one depends on what you want to communicate and what the story is. So there's not really any science that says you should show the plot on the left or you should show the plot on the right. But you should think about which of the 2 plots you want to show. do you want to emphasize the difference between January, July, and October? Do you want to emphasize the periodicity, saying, oh, in summer you made way more money or something like that? Or do you want to show how the global how this globally looks over the year, and basically you can say, oh, in July I made way more money, or you could say most of the year I made around 30K. And both are true statements, and it depends a little bit on what you want to focus on. All right. Wow, my timing is good today. Yes. Or maybe, hopefully. Another thing I want to talk about is 3D plotting. So here is a great example from the Matplotlib website, which shows the Lorentz attractor. So here, to do 3D plotting in Matplotlib, you have to import this guy, mpl toolkits.mpl mplot3d import access3d, and then never use it. You have to put this import in, and that's basically it. You also have, for your axis, you have to set the projection to 3D. If you do these two things, the import and the projection, then you can plot 3D. So here, what used to be a 2D line plot, now plot is a 3D line plot. So, and it looks so cool. The thing is, so you can do this with plot and also with surface and with scatter plots. Here's a scatter plot for the iris data set. This does it slightly differently, but again, I do this import, and then I add a subplot, 111, which is like, I just have one subplot. This is an easy way to add a subplot with a projection 3D. Oh my god, my battery is empty. The thing is, if I now look at this, this is just a 2D projection again, right? So I made a 3D plot that has 3 features, which are the 3 first features from the iris data set, and then I made some random 2D projection of this. Depending on how I rotate this thing, I get a different 2D projection. I don't really need a 3D plot to that. I can, if I want to compute a 2D projection, I can just compute a 2D projection. And this is a very arbitrary 2D projection. I don't know why this one should be good. So in like in data science, you often have high-dimensional data that's often like weird point clouds. And if you look at a point cloud, usually visualizing them in 3D doesn't give you more information. One way it can give you more information is if this is interactive. So if you can turn this around and play around with it, maybe you can find an interesting angle. But just doing a static plot like this, or plotting something like this in a paper, it's completely useless. Like, this is not really a 3D plot. What is the 3D in this? You have this 3D coordinate system, but it doesn't give you any information, really. So usually, I would argue you should avoid 3D plots. This is not the worst possible. You could do worse, like this. This is also from the Matplotlib documentation. So it tells you how to do this. Just because you can doesn't mean you should. So this is a 2D bar chart, and I think it's terrible. You cannot see what's going on at all. You could easily do this as a heat map. So exactly the data you could show as a 2D heat map, because it's like a 2D grid and there's a value for each point. Or you could have several slices of histograms. And so having this kind of 3D really is not very helpful. You can go even worse like that. Sometimes in magazines or online you will see people doing 1D bar plots that are in 3D. So basically just one of these rows. That's basically the worst you can do, and violates most of Tufte's rules. I think he pretty explicitly says never ever do this, because there's like so much stuff to it that has nothing to do with the actual data. Yeah, just don't do 3D. Wow, and I'm finishing nearly exactly on time. So a couple of do's and don'ts summarized. Definitely always take your time. Unfortunately, a little bit because of Matplotlib, but also because you need to really think about what you want to show and how to best show it. It takes time to make good figures. So always take your time. Label everything and think about why you show the figure. What is the point? What do you want to illustrate? What is the question you want to answer? Don't use 3D unless there's like a really good reason for it. Usually, don't use pie charts. There's like some rare cases where it might be helpful, but usually it's not. Don't have things that are, like, don't have non-varying ink. So don't have a lot of stuff that have nothing to do with the data, like a 3D coordinate system if there's no 3D data. Also, not so much for inside Jupyter, but if you publish something or if you write a report, don't edit your figures manually. Matplotlib will allow you to do anything, and if you edit your figures manually, it will be basically impossible to reproduce however you did the figure. Also, it means that if you figure out you had a bug, you will not redo the figure because it was too much work. If you did it all in the program, you can just rerun the program. So here is a couple of resources. So the first two are basically classical books that are a little bit outdated, but or let's say they're dated, but they're not outdated. They're interesting to look at. The third and fourth are both free online. So as I said, the fundamentals of data visualizations. I haven't read all of it, but it looks really, really nice, and it's free, and it's like brand new by Klaus Wolke. And then the Python Data Science Handbook on all of the Matplotlib stuff. There's also tutorials on the Matplotlib website. They're actually like mostly way more advanced than what we talked about. Some of them are way easier, and some of them are way more advanced. All right, that's it. Thanks.